So, welcome to the lecture on vehicle motion planning, the survey of approaches. So, it's more general perspective and remind you. So, the problem we're talking about is how to create a path, trajectory in time, a path, if we make time explicit, that characterizes a vehicle's motion, could be a robot arm as well. So for the vehicle, it will be in the 2D world, so a position in the world, including the orientation of the vehicle, that it fulfills constraints. And the kind of constraints primarily are actually obstacle avoidance. Ultimately, of course, going to a target, maybe a target configuration. You can have special constraints like in docking to have the vehicle in particular order, orientation. And then you could even have via points, like a sequence of targets that would be via points, right? That's not so common. But the main problem is really avoiding collision. And that's when you look at the motion planning literature, that is what it's about. And so what I'll be talking about are methods, methodicity. I first introduce briefly classical planning approaches, vehicle in the literature, that will be 90% of the literature, and then present the potential field approach, which you already encountered a little bit in this book chapter paper some of you read, and I'll compare that to the attractor dynamics approach. In fact, following that paper, so some of you might have already read that. Briefly review Bornstein and Koren, which is an approach that is sort of like the attractor dynamics approach, and then about extending the attractor dynamics approach a little bit. And the last thing, actually, the order is a little bit different now. The dynamic window approach as sort of a special or an extension of the attractor of the potential field approach. I think I have moved that a little up. So let's first talk about classical path planning. So here are some references. La Tombe is the classical book about that. It's like 1,000 pages. I'm not sure it's available online, but Laval's books are actually online available in a preprint form, so officially, not illegally. So you can Google them. This is the new edition, 2010. And that's interesting. Maybe most of you get a survey of everything that is there. It's also a 1,000-page book. I actually also found very useful the chapter that Laval wrote in the Springer Handbook of Robotics. This is the latest edition, 2016. It's 2,500 pages book that covers everything. Actually, in the last lecture of this course, I will briefly show you the table of contents so that you know what you've learned now of all of those things. It's a small sample, of course, but you will be able to orient in that book. So that's just the point of the literature. I'll be referring to some of Laval's graphs here. So here's an example, so schematic of what the path generation of path planning problem is. You have, this would be for a point-like robot, like a lot of approaches to that. A point-like robot has to go from an initial to a final condition, and it would have regions in 2D space that are designated obstacles, like here these polygons, and there the closing in the robot is done by defining obstacles on the outside walls, and the robot would be able to stay in this arena, and then a solution to the path problem would be a path. So a path could be a closed set in 2D that can be parameterized. That would be time, right? When you control speed, you control how fast you go through that path. But the planning problem is really just the spatial layout of that. Later in robot arms, we will see that the timing problem, when to arrive in time, is a separate problem that is interesting. In classical robotics, not so much, but you can imagine if you want to catch something, you have to be at the right time, at the right spot to catch it. Something that moves. So you can see that this sort of approach will assume something about the world. So in a scenario like this, we would call that a global approach, because you assume you have the layout of the entire world. There are some approaches that one would call classical, in the sense of computing geometrically, that are just based on local information. That's a special case, and I'm not treating it here. For instance, parking is an example like that. When you make these parking maneuvers for a car, you do path planning based on understanding geometry, but typically you do it in just based on the local depth profile. So that would be a local. So here is just a pointer to concepts in this field. So very often people talk about configuration space as a way to do that. Configuration space would be the space that characterizes the degrees of freedom of the robot. So what you can achieve for the robot, and express everything in terms of that. So for a vehicle, it's very simple and intuitive. This is an example of a triangular robot. These theoreticians use these funny examples. The triangle robot, right? Usually a robot would be not structured as a triangle. It's described as a polygon into the outer perimeter. And a triangle is just the simplest polygon that you can do, if you think about that. You know, less than 3 would be just a line to make it something that has a finite volume. You would have a triangle. So this is the robot triangle. You have some coordinate for that robot, and this would be a square obstacle. And so configuration space means that you now compute, based on the information from the world, from the obstacle, all the possible configurations of the robot that would not be allowed, that are not that have to be avoided, right? That are not allowed to avoid collision. And so you can see that this would be an example that you can shift this around, and you have to keep a certain distance, right? So these sidebars are the ones that define the obstacle in configuration space. A simple example. Now that is something that is really useful when you look at arms. You can do the same for a robot arm and have 7 degrees of freedom. We'll talk about that just down from now. And then that's like 7, 8, depending on the number of dimensional space. And you have obstacles in the world. And you could express these obstacles as all the configurations of the arm that you want to avoid. Like, for instance, avoid contact of any point of the arm with an object. You can see that can get complex quite quickly. And in fact, computationally, this is a very demanding problem. It's even characterized in terms of computability as a complex problem. There are some theorems about that. So this is from the book of Laval to illustrate that difficulty. People talk about the piano movers problem to characterize this motion planning problem. It's more in the intuitive sense, right? If you are you move a piano down a staircase, you can imagine that it's complex operation, which angle to take it so that it can go around the corner, right? Some of you maybe have moved something not quite as heavy as a piano. This is a robotic demo where actually a grand piano is carried by some mobile robots and in a busy room. And to illustrate this idea that to avoid contact with any part of your object here of the piano, with any part of that scene, is a complex computation problem. As you could imagine, you have to search for points of contact every moment in time, find mathematically the minimal distance that you have, and so on. Very complex, and in a certain idealized sense, it's true in computation. It doesn't scale well with the number of constraints that you add, the number of surface elements. So I'm not going to go into detail about that. So it's a huge mathematical literature. Because it's so complex, it allows you to do a lot of interesting math. And that is actually really still a bottleneck in the sense that solving problems of that nature computationally is costly in terms of computation time. If in a lot of scenarios, you have to do that multiple times because the environment might change, and you want to each time you have to find, is the path still viable? And so, for instance, for robot arms, this planning problem is still so severe that there are actually some companies that offer a special purpose hardware, computational hardware, to do this in real time, to do this fast. There's hardware that's particularly designed to solve computational problems of that nature. So it's surprising because you think, oh, that's a very old-fashioned thing, but it's still a major topic of research to do this under conditions of autonomy, to do it fast and in real time. So one popular approach is what's called sampling-based approach, where you have certain islands in configuration space around which you can find good solutions, which consists of approximating your obstacles by smooth surfaces, for instance, and then you can do some geometry to say what kind of configurations are adjacent to that, just at contact. And then you connect these islands with some heuristics in a graph, so-called roadmap. And I even don't understand myself fully these approaches. So I'm just to highlight that's the sort of thing that is out in that classical literature. And that's an approach where there are variants of this that are global, so they know the entire environment, and exact. So there are approaches that actually prove under certain circumstances that the system will find a path if there is one. So very mathematically. Everything else is heuristic. And so the potential field approach, with one exception, is a heuristic approach that you already encountered and is really quite popular as a talk solution that is computationally much less demanding. See purpose. Maybe get an intuition for how effective that could be. So it was originally, I believe it was invented by Usama Khatib, who's now at Stanford. He did that work actually in Toulouse in Toulouse. I think it did in Toulouse, which I actually happen to have collaborated with these guys at the so-called LAS Institute there, like 7 decades later. There's actually a related Mental Hogan's impedance control approach, has some formal similarity, but priority seems to be really Khatib. And so we contemplated earlier the idea that you would have a vehicle or a manipulator. He actually formulated this in general form in configuration space, so it covered both arms and vehicles. The moves in a potential field, which you erect, and the idea is you have some algorithm that would go downhill in that potential, or you can also define everything upside down if you want. And so it's the model that you use is the one that builds that potential field from components, and then the algorithm is to go downhill. And there are different variants. So first of all, there are variants of how you model the potential field, how are obstacles and targets represented mathematically, and variants, how do you go downhill there? So straight downhill, or with some smoothing that you sort of have an inertial term, so you don't turn on the spot, you turn slowly and so on. And there's a whole literature on that. So this is from the original paper. This would be an example of how an obstacle for a vehicle would be modeled potentially as a little hill that repels, right? That you go. So quite abrupt, actually, the way it's defined here. That is actually something that you find. If you make it too smooth, then you're influenced by the obstacle, and that limits the range over which you can act. And then there would be an analogous possibility for a target contribution. So here's from the book chapter examples of a target component. And a target component would, for instance, define a minimum position and going downhill everywhere. So typically you want the target term to be soft in the sense you feel the gradient, right? The approach is sensitive to the gradient for going downhill. You feel that gradient across the entire space, so you always head to the target, while the obstacle component is supposed to be localized, so that if you go far enough from it, the gradient is no longer dependent on the obstacle. So for instance, here the spatial fall off of these terms would define the spatial extent of the influence. And then the potential that's used is just the sum of these contributions. Very analogous to attractor dimension, we sum the forcelets. See, the difference is what kind of variable you're using. This is in the configuration space of the robot. It could be, let's say, for a point-like robot, it could be just the position of the robot in the plane. And you're going downhill means you're moving in the plane in the direction of that global minimum. So when you are in the attractor, potential field is a special case of dynamic system, so it has attractors. The gradient descent could be viewed as a dynamics. The attractor would be the target. So when you are at the target, you would be in the attractor, right? So we've argued that in the attractor dynamics approach, you are in the attractor all the time in velocity space, and here you are only in the attractor at the final point. Yes.
Is this actually three-dimensional, or is this only for visualization?
This is the third dimension is the potential. So this is over the plane, and the third dimension is.
So there is no fourth or fifth dimension. So
this can be applied in higher dimensional spaces. That is, so a potential. Maybe I should have explained that. So potential is a scalar field. It's actually like the neural fields that some of you might have heard in the other semester. So it's one variable, the potential, no, the value of the potential, defined over the space that you're looking at. So if I have a point like 2D robot, then that space is just 2D space Cartesian position of the robot, of the center, let's say, of the robot. But more generally, it would be a configuration space. So for a robot, it could include its orientation. That would be a three-dimensional space. And it could include, for a robot arm, it could be as many joints as it has, so seven-dimensional space. So then you have a one variable defined over a seven-dimensional space. It's called a scalar field because the field itself has just one dimension, it's just the potential. But if you remember physics from high school, I don't know where you would have had that. Remember, the electrical field is a vector field because there are three numbers that you need to characterize the field, the vector, and that's defined over 3D spaces. Three number over three numbers, that's a vector field. A scalar field, there's actually the electrical potential. You can derive the electrical vector from the electrical potential under some conditions, and then that will be a scalar field of this nature. That people are using the electrical fields or the electrical potential as a way to model these kind of fields. I mentioned that in a moment by solving essentially Poisson's equation. And then it's not easy to visualize, of course, if the underlying space is so high dimensional, right? Then you just have your algorithms how to go to the minimum. Does that answer your question? Yeah. But, so these cases are just used because they are easy to visualize. There are these famous problems. So their so-called local minima, there's an intuitive picture of that. So for example, an obstacle of this nature, the target is behind, then there can be a minimum here that isn't the minimum you want. It's not the minimum at the target. It's a local minimum. And that's a problem, is the approach will end up getting stuck there. The motion planner gets stuck there. That's a very generic problem. It might be intuitive that it's generic. Here's another instance. If you have a obstacle, a target, and there are two obstacles, this is sort of stuff we looked at in the attractor approach, then you might be pushed against this here. But if, depending on the spatial fall off, you could not, it actually goes uphill between those two because the ridges of these two obstacles overlap, and then you couldn't go through here, but you also can't go away from the target. So it's the analogous kind of thing that happens.
Can that also be solved with like a stochastic component, like as we did?
Exactly. So there are a whole bunch of ad hoc approaches. These approaches are very often realized computationally on computer. They're not dynamical systems in our clean mathematical sense. So people have things like that they have a algorithm that monitors if the robot makes enough progress in space, and if it doesn't, they say, oh, I must be in the local minimum, and then they do some random perturbation, put it somewhere else, for instance, or put a new via point somewhere else, and so on. So there are approaches like that. The local minima are somewhat generic. Maybe this might even give an intuition for that. So for instance, here you already have that feeling. If it goes downhill, you can think of this like a mountain valley, like the downhill is a global thing because you want to be attracted to the target. And then if you have any kind of obstacle, if it lies in that direction of the valley, there's a little lake forming in the mountains. It will be a mountain lake that forms, right? Obstruction in the downhill valley. So in a sense, it's very generic. It does happen quite a lot. And that's why methods to overcome that are in demand, and there are approaches. I'll mention a little later that potential field is often used in the context of a global path planner that has these classical exact methods, so-called deliberative planners, that make actually algorithmic planning at the global level, and then they use the local field potential only at the local level, and you can have algorithms that go back and forth there. So they notice there's some problem, and then they do a new global plan, like make a new via point, and then holistically go there. It's then, typically not exact, so it only works a certain percentage of time. So this is just a hint that it can be done in high-dimensional spaces. To be an example of academic example, right? A arm in 2D, but with a lot of different joints, and then you can make complicated configurations where this arm would have to find the opening to get to some place. You as a human would possibly have a hard time doing that if you put your arm into some tube to unscrew something. And the power of this is that you can express these constraints all locally, with repulsive surfaces in the configuration space, and then can find solutions to that, which would be, if you do that exactly with geometry, would be very challenging. Now, this is what you read, I think, the Fajan-Warren application. And remember, what they did is that they used a potential field model, generic potential field model to fit this human data, and that they also fit with the attractor dynamics approach. And then they discussed a little bit the properties. That part of the paper, I don't know, you were not tasked to actually read that at the time, right? I just directed you to some parts, but maybe you read it. It's actually, frankly, not so easy to follow. I think this paper is not optimally written in that part. So it's not quite so easy to figure out exactly what they're driving. And also, we don't have to fully understand it. We actually studied that for a while. We interacted with those guys. So what one can say, certainly, this is one example. This may be the best example. These are what they call the typical path. That is, if they took the models that fit the human data reasonably well, and I think this was only done by hand, that looked good. And then they varied configurations, which are not exactly the ones in the experiment. Experiment with the human, remember, had only one obstacle at a time. It was very simple. But when they then put in some more complex obstacles, then they could sort of analyze what happens. And here's an example. So these 5 obstacles here drawn as points with circles around it would be what defines these repulsive forces. They had 2 factors: how big a inner cylinder is, and then how strongly the potential falls off. That would be like the safety margin, how close you get in a soft way, and then the cylinder is where you're supposed not to ever penetrate. So if you did that, then the attractor dynamics approach was doing this path here, the path number 2, to the target. So initially turned to just a question of the initial orientation, somewhat reasonably, and went relatively straight. And the potential field approach has this feature that it makes somehow these abrupt maneuvers. You could perhaps see that what happens is that when you are feeling the gradient, then the contribution to the target is quite small. So you're really going sharply away from the obstacle, and is ultimately orthogonal to the surface, right? The gradient would be orthogonal. It's the direction of steepest descent. So that would be orthogonal to equipotential lines, which would be the circumference of the obstacle. So it has a somewhat exaggerated maneuver feature that did not fit the human data so well. And remember, they even introduced this inertial term. So the human trajectories were even smoother than the first order attractor dynamics approach, suggesting people don't turn so abruptly. So in that sense, they said that wasn't so realistic. And they varied then different aspects of it. It's essentially just the same point amplified. So they varied how the spatial fall off of the potential is compared to how the spatial fall off of the attractor repeller term in the repeller term actually in the attractor dynamics approach was. And for the attractor dynamics approach, you could have smooth influence, and that would lead to smooth paths that are still successful. And so that's just another illustration of the somewhat abrupt nature. Interesting comparison is this difficulty with the local minima. So they suddenly demonstrated that possibility. So when they had this potential field that was approximately right for the human behavior, then they put it into a configuration where there would be a whole series of obstacles here. And then there was a local minimum, which showed up in the robot here circling around, because the speed wasn't controlled. It was a constant speed. It would not stop. It would just go in circles randomly in the local minimum that had formed here in front of the goal. And the attractor dynamics approach could also have a problem under some circumstances here. So for instance, here, this would be a path that goes between two obstacles too close in terms of the size of the vehicle, right? It would collide. That would be not a correct path. We used to call that spurious attractor, so an undesired attractor that does not fulfill the constraints. So attractor solution is violating the constraints. While if you make the obstacle influence parametrically right, like broad enough, then the attractor dynamic approach would actually make a very smooth path around the whole thing. So in that sense, it can solve that problem and not have a local minimum. So actually, the problem in attractor dynamics does not manifest itself in the terms of these local attractors, but spurious attractors, meaning it's an attractor that violates the constraints, or moving within that violates the constraints. And it's intuitive, and actually in our original paper where we proposed the approach, which was done with Michael Dose in 1992, I believe, we actually studied that problem and analyzed that problem and proposed. So the problem arises from cancellation. Actually, you just have a graph of that, and I didn't include it in the talk. Remember, any individual forcelet has essentially, has a repeller at the direction of the obstacle, and then it has, a positive term for, it's actually the other way around. Negative turning rate for going away from that repeller on the left, and the positive one on the right. So you could say it's pushing away from that obstacle by having the turning rates to that right. Now, if you put another obstacle at the appropriate distance, you could see that what could happen is that when this one has a negative turning rate to get away from this one, that could be overlaid with a positive turning rate from the other obstacle because you're on the other side. So the two could cancel, and you have something flat. And if you're unlucky, it might not even be flat, might even make a little attractor there. That's a sort of form of cancellation. And that's particularly bad if you have a lot of obstacles. If you could see that then if you sample them densely, you could arrange that for every contribution that puts in one direction, you have a matching contribution somewhere along the sample that it overlays exactly with that repulsion and cancels that term. And that leads to these kind of solutions. I refer here to those. Sure, I didn't want to explain that in detail. It takes a little more effort to do that. And so what our solution then, we actually provide an exact solution for that, is to say you are going to arrange parametrically that the superposition of these two obstacles works for two obstacles. Remember, that's the instability that we studied in the subsymbolic version of the approach. That is, when you're having two obstacles, two repulsive terms, and you vary the distance between those, you arrange that the transition from having a attractor to a repeller happens exactly at the distance that's compatible with the vehicle size. So just as you cannot pass through it anymore, you want the two repellers to fuse into a single repeller. So that would be how you control the cancellation. What is then not guaranteed is that if you add a third, fourth, and fifth contribution that are close, overlap, then you still get cancellation, right? And that will be more and more constraint equations, more than you have parameters, so you cannot guarantee that. And our solution at the time was to say, what you should do is you should select the obstacle contributions that you're going to take into account. That's something else, okay. Yes?
So does it mean the example for the robot? So the example robot for which we are writing currently writes the essay has a certain amount of sensors, and they are at a certain degrees apart. So that is not just random. This is like a hyperparameter, which we need to choose according to the diameter of the robot.
So the way you're asking the question is a slightly different problem, because that was what we called the subsymbolic approach. That is where the number of contributions and their nature is just determined by your sensors and sensor information. And then it's actually a different problem of how to deal with that. While in this context, it's a symbolic approach. That is, we're talking about the number of obstacles in the world, right, symbolically. And the approach I'm mentioning is one that would work in this domain. That is what you would be doing is what you would say, I'm going to select two of the multiple different obstacles that I have, the two most critical ones that I'm close to colliding with, and arrange, and I've arranged that two contributions are always tuned to have no spurious attractors. And therefore, then the ensemble will also have the right attractors because it's only two. And as you move, that might change. As you move, you get closer to a third obstacle. And now the critical ones are two others. Let's say one of the old ones plus the one that you got closer to, and you discard the one that you are now far from. And then again, you have arranged for that to have the right attractor structure. So that's what we did in that old paper. And we actually used some kind of a neural network type method of selecting the right obstacle. So also did that automatically rather than have an algorithm to it. We had some kind of dynamic system that was a neurodynamic system that was selecting always the right obstacles in this sense. If you do this for the subsymbolic approach that you were referring to, there's a way of sampling that's automatic. So I was hinting that just selecting relevant obstacles would be the ones you're most likely to collide with, right? And you would have some way of algorithmically or with some dynamic system doing that sampling. Now, when you have that the obstacle terms vary with distance from the obstacle, then it will be automatic that those that you are in risk of colliding to are the closest one, and therefore the ones that have the strongest contribution. So the idea would be that you would ultimately only face one obstacle, the one that you're one obstacle, let's say it's the sensor, right? So only near one sensor you risk collision, because you have a spheric robot. So it would touch any surface that has a curvature larger than the robot at one point. And that sensor closest to that point will dominate, and then you have the correct repeller. Or in the worst case, you could have 2 points where if there's some symmetry, 2 points where you would be potentially colliding, and then you would calculus make sure that it still does the right thing for these two sensors having the minimal surface. That's a heuristic approach. I mean, there are, so when you do it this way, there are, of course, configurations where you still could collide. These configurations have to do with the limits of your sensors. Imagine if you have a very spiky surface, like a wall, but there are some spikes coming out from that wall, and your sensors will be only to a limited extent aware of that. And then you could have that, you're touching 3 spikes, so multiple spikes, and your sensor information doesn't do that well. And that's a limitation just of having this kind of crude approximation to depth. There is actually one configuration that you can create for all of these approaches to fail, and Michael Dose, whose doctoral thesis was about this, actually did design that. So a funny anecdote. He did this in a simulator. So this would be if your robot is surrounded in a circle by obstacle at the right distance, so that they all have the same distance from the robot. They all cancel. You can't really select the right one. Then you would have perfect cancellation. You go through the wall. And he actually wanted to demonstrate. I had all kinds of arguments why that shouldn't happen. He said, "No, it happens." And I said, "Show me." So his simulator was running somewhere else at the time, so you needed a better computer for that. And so we went to that other lab where the simulator was running, and he told me, "I have to set this up first." Why I say that? He was a very gifted programmer, so he had made a graphical interface. Today, you think that's trivial, but at the time it was quite innovative. So he could position graphically the robot in a landscape. And it turned out that he had to position by hand, by the mouse, to click. And it was so special that he had to find the exact pixel where to put the robot, because only if you put the robot into that pixel would actually that cancellation happen. And that reflects that the configuration is one, that you wouldn't be able to get into. How did you get into that circle to begin with? So it's an example of, really doesn't matter at all in real life, but mathematically it's true that you can have cases where this fails. And so analogously with sensors, you could have the same thing, that if you're in a configuration where you're simultaneously colliding with continuously many points because the surface is exactly the radius of your vehicle and you're approaching it exactly symmetrically. Actually, you have to already be in that position, then it will collide. So these are academic games, but actually the path planning literature is a bit like that. They look at these, really proving things and excluding that something like that can happen. But for heuristic approach, it's really not a problem. So I'm not sure. I didn't document this. There's a lot more graphs to show, but that takes a lot of time to understand. So I just essentially say attractor dynamics has this potential for spurious attractors, but there are clear countermeasures. And in the subsymbolic approach, it actually really never really is a problem. But in the literature, actually, it was discussed as a problem. So Fagin and Warren actually thought it was a problem. I didn't think that it's really true. Yes.
Yeah, the thing about the example from before, that one. And so why do they cancel out each other here? Because the one obstacle is that remains around it, and then the other obstacle next to it will lift it even more.
So for instance, here, if you only use this and that contribution for the obstacles, then there would be a repeller in the middle, you would go around it. But because there are more contributions, they all overlap, you have that cancellation. The online people won't see that, but I'll make this drawing really straight that. So actually the turnaround, but now I don't even know how to do that. So remember, let's do it this way. Right? So this would be one obstacle, right? And now let's say you have multiple obstacles, for instance, like this. And maybe you get an intuition that now there would be what would be the sum of these? So the sum of these would, go, let's say here, for instance, here you would have this would be 0, and that would be 0. So here you have 0 already. This plus that, this goes to 0, right? So what would happen would be something like it goes to 0 here, something like that would happen as a result. So this 0 here comes from, someone on the right providing always the opposite to someone on the left.
So we want to find that around these two obstacles and how it's going to be.
Can you say that again?
So if there were only these two obstacles, it wouldn't go try to go between.
That's right. When you have only two, you can mathematically arrange with the width and the parameters that the transition between going through or going around happens is exactly the right distance where the vehicle fits, right? You have these width parameters to control that. That's what you mathematically arrange to be the case. So in that sense, you wouldn't have a problem with just two. But if there are more than two that contribute at the same location because of the range, then you have a problem. So with Michael Dosis, at the time, what we had an algorithm running if you approach a configuration like that, where it would determine that only these two are the most relevant, and it would make the width of the contribution of all the others 0. It was a dynamic system, so it was that if you're now turning, then this one would be turned on, and that one would be turned off. So it would be dynamically adapting which ones are selected. That's our first paper about this approach. We already introduced that kind of complication. That was a little hard to understand, but it just actually really works. Does that answer your question?
What would be about just making the range of the obstacle so small that it's you never have more than two overlapping obstacles?
Yes. So if your angular range is such that the obstacles don't really have an influence on, like all the outer ones don't have an influence, then you shouldn't get that spurious attractor, and you don't actually. So some of these problems can even also just be solved by choosing the right parameter values. Frankly, Fagin and Warren didn't do that very well. So they were more interested in qualitative things. So even without this sophisticated method of activating, you could minimize the problem here by choosing the parameters right. But we, it's more of a, I mean, they did this just academically in simulation, right? If you do this in the real world with a real robot, this is a bit of a problem. In the real world, you don't really have actual obstacles. You have some sensory information about obstacles. And now that I hinted, remember I showed you this awkward vehicle going around some plants. It was actually in the laboratory space we had back in the other building. And that detected obstacles in the sense of points in the plane that stick out from a surface. And these points are not necessarily, they might come from the same physical object or from different objects. And every measurement of that nature counts as an obstacle. And so you could have a situation, for instance, a typical situation where this kind of thing arises is you have an obstacle here and I have an obstacle there, and there's a small obstacle in front. And so you really can't go through. But you have a lot of sample points on the obstacle on the right. So a lot of forcelets that are superposed make a huge repeller there that push you toward the middle. And you have a lot of samples on the left, which make a huge repeller there, push you in the middle. And you have maybe only 1 or 2 sensor points in the center that push you away from that. But they will be overwhelmed by this influence from the sides. And that was a realistic situation that happens. And so the approach is then still selective, say, this is closest, even though it's just one, I'm going to just select the one. And then for all these other data points that are all overlapping, I'm going to select a representative one. That's what we did. We just took the one closest to collision and suppressed everyone else anyway. This is similar, you will see in a moment, to the Bornstein core. And so it's a problem many of these approaches face. You see, scientifically maybe interesting. The way you academically work is to divide the problem up into subproblems. So this is the motion planning problem that is studied separately as a whole field, and people have their own conferences or at least their own subcommunities. And on the other hand, the problem of how you know about obstacles, that's about sensing or about perception or world modeling and so on. It has its own discipline. But the two interact, because if you use a certain approach, then it will act differently depending on how you get information about obstacles. Abstractly, you can talk about obstacles, but with your world model, it might be just a sensor reading that you interpret as an obstacle. And so this is a challenge in this field, that the approaches in different subproblems depend on assumptions you make about other subproblems. And there is no universal solution to that. That's why it's so complicated, why there's so much work on these things. Our approach was actually one aimed at using a unified language across all these different domains and using dynamic assistance for everything. What I'm just hinting at, selecting a representative, was an example of that. And we're not pursuing this seriously in robotics, but dynamical field theory, which I teach in the winter semester, is actually aimed at that, namely aimed at creating unified languages in which you understand everything from sensing, perception, memory, decision-making, sequential planning, to ultimately motor control, achieving goals. We do that not around robotic vehicles, actually more typically around reaching, handling objects, making certain kind of cognitive operations on scene representations on the world. Well, so that is a problem, that these different parts of an autonomous machine depend on each other. That's something called the integration problem, and that is a very characteristic of autonomous robotics as a field. Well, the clean stuff, like I have a very clean mathematical problem for motion planning, just make some assumptions about the world modeling and maybe also the control, the other side of it. And then, don't have to deal with the dirtiness of there, but it never really works. So the classical approaches with these polynomial works really only work in simulation pretty much. Good. I wanted to mention about the potential field approach that there's also a real workaround that I mentioned these ad hoc approaches, right, where they have an algorithm that detects the problem and so on, which is state of the art. People are using these kind of tricks. There was a proposal in the literature in the 90s for how to solve that problem in general. It's called the navigation function approach. There's someone called Korychek who did that, who became famous later for related ideas, actually very interesting ideas. So the navigation function approach would be say, well, the problem arises because we're just combining these, we would say forcelets, these little potential field terms, right? These little hill, little valley, and then if you just combine them, you can have that the combination doesn't fulfill the constraints of the individual terms. So that, well, instead what we should do is we should compute the potential field such that it has exactly the right minima and maxima. So it only should have minima at the target, maybe the multiple targets, and should only have maxima at the obstacles, and no, undesired minima or maxima. And you could write that down mathematically and then compute the potential for that. And that would be called what they call a navigation function. Just use that term. And that can be done. An intuitive example that was actually used by them at some point is the electrical fields. So if you know physics, you might remember that the electrical potential, we have charges, point charges, the electrical potential, that's the solution of the Poisson equation. That's the Maxwell equation in the static case. In the static case, it becomes the Poisson equation, and that electrical potential has maxima at positive charges and minima at negative charges. So you can essentially treat it that way. You put these obstacles at, treat them mathematically as charges and the target as negative charges, so the other way around, and then solve the Poisson equation, then you get a potential that has exactly that right property. Now, you can imagine you have to get the spatial scales or some other problems with that, but you can do that. And then you have an exact potential that is now you will always fulfill the constraints when you're going downhill. Immediately, I don't know if you know anything about this sort of physics, you may know that is actually a computationally also very hard, to solve the Poisson equation all the time, because you have to update that every time there's some change, and sensory information about the world will make there some change. So just computing the potential is hard. And then there are people who are saying, we don't have to compute the whole potential, we'll just compute it in a little region that's close to us. And then it becomes a heuristic approach again. So this was not actually successful in practice, but it was like a nice academic example. There will be their theoretical excuse for how that's still a good approach. So just mention that more historically, you will not see that people really use that in this way. So people use the potential field approach as reactive planners, and very typically as just one little thing in an architecture. So they would have a architecture. This is from one of Arkin's papers this year, Ron Arkin, who works a lot for the US Army. That's why not everything is published that he does. So they have done much more recent stuff that's more advanced, it's not published. So in these systems, they would have, very high level things, a mission planner and all kinds of, AI style stuff, all based on world models, propositional knowledge, and so on. And then the lowest level is putting down, your next target point. They have all sequence of via points, target points, and so on. And then you would have a local level approach that essentially then smoothly acts based on that. So it takes the sensor readings and then does the fine tuning. And that's where the potential field approach would be used. And he has these things. I think I might have some slides here. Yeah, this would be another rendering of that. And they can do more than obstacle avoidance here. This is an example of the kind of things that they use at the lowest level as vector fields. So for instance, this would be a field. This is the vector field this is the gradient of the potential, right? You can imagine what the potential looks like. And here, this would be one that makes you stay on the path. This is a attractive one, I think. There's an attractor in the middle. This is a repulsive one. And this is sort of a docking one, which tries to push you to approach in a particular orientation. And then the superposition of those will make that you do the corresponding thing. So this is not exact. It has all the problems that we're hinting at, but it would be only the local planning, and you would still have a global thing that sets these different goals as modules. So I don't want to go into too much detail of that. This is, yeah, well, I skip that. It's actually, I wanted to skip that whole part. So literature has developed for doing these sort of things, and when you do that, some of the complexity of behavior can be done by almost activating these little, you could say, little force fields, or these little, they call them schemata, comes from psychological theory for that. And there are actually people who developed here in Kaiserslautern, it's a group who developed a whole programming language and design to do that. So they have it's strictly behavior-based robotics. That is, every module, which is a behavior, gets its specialized sensory information that is required for that, and it generates specific motor output. And everything else is really just done by activating or deactivating that module. So you can turn on or off a behavior. But in other words, behaviors don't interchange information, sensory information that isn't specific to the vehicle. So for instance, these individual behaviors, we call them behavior, each box. They do not just use a world model and grab stuff from a world model, like shared resources. And then one can then build kind of a behavioral logic sort of things that where different behaviors give each other sensory information. Subsumption idea that rather than get it directly from something, you could get it from another behavior, and you can build a huge architecture. So this, for instance, arbitration between multiple different behaviors where you determine which one you're going to do, or this is also another kinds of arbitration and winner take all and large complicated thing. I think I have one slide here. No, I don't. I had a slide at some point. These guys built architectures like that are it's actually for human difficult to even analyze, so based on these local ideas, and that does work to some extent. It is, I mean, they can program. They have some hardware vehicles like this, and they have programmed these systems to show meaningful behavior of considerable complexity, I would say. There are really two disadvantages. One is that understanding, designing this understanding what the emergent properties of this is not easy, and sometimes really leads to surprising effects, so not anticipated effects. And this problem really arises with true cognition. So when you're trying to behave in response to not the immediate sensory information, but something that we would call knowledge, that you, from memory or from some other state, you know that you had some perception earlier and you knew there was an object there, and now you want to take that into account in your planning, your reach or so. And this system isn't very good for that. It's not in principle that you can't do it, but it's very hard to achieve that. So I would say it's sort of, in a sense, it's kind of a dead end road now. I don't think it's very influential right anymore, but you can push it quite far. And that uses the schemata idea, glorified version of the potential field in a sense. Yeah, it's a bit ambiguous. This is the problem of these kind of lectures, that to fully explain that, of course, would take a whole hour. So it just gives the flavor of the sort of thing people do there, right? It doesn't really explain in detail. Good. So that's as much as I wanted to say about the potential field approach. It took a lot of time. So you're not expected to understand the details of the potential field approach. It's just get an impression. So the potential field approach is still the most used reactive component of vehicle motion planning. So low level, and there's a potential field filter that integrates a few constraints. You can see that if you have other kinds of planners or behavior organization, or behavior-based robotics means you don't have a algorithmic, symbol-based planner, but you have this complicated, all possible ways to behave, and you select the right one. And you've designed all the different ones. So one for going around corners, the other going in corridors, and one maybe for approaching an obstacle that you have to get close to, like a near planner and a far planner. So for all of these, you have your little planners, and then you're activating and deactivating the correct ones, right? That's sort of the idea. And so with that context, potential field approach is very much used. Dynamical attractor dynamics could be used very well and would be better. We've demonstrated that occasionally. It's not used as much. And it is, I think part is because we're not so active in robotics and not pushing this more at the conferences. But I also think it is somehow mathematically a little less intuitive with the attractors, the bifurcations and so on. And the potential field is very intuitive. You look at this, just say, okay, going to superpose this thing, where does it go downhill? Makes more intuitive sense. And this has to do with the variable that you're using, right? When you're using attractor dynamics, you have to think in velocity space, and also this of one derivative higher, so you have to more abstract. While here you think in configuration space. So it's quasi postural. You're essentially setting a sequence of postures as your goals, and how you get from one posture to the other is then done by the approach, but you don't think about that in terms of state variables. Good. The dynamic windows approach is also somewhat popular. I don't know how often it's really used now, but it was very popular for a while. And it is a extension of potential field thinking into the time domain. So not just taking into account the path, but really how fast you move in them. For vehicles, it was attractive just to be able to move a little faster. In many cases, the vehicles were moving somewhat slower because the path planning is heuristic, and you want to update your planning as you get closer to stuff. And so you want to have enough time to do the replan. So it was in that sense, quasi-postural sort of heating. So to take into account time when you do the planning, it allows you to push the limits, and that's what this really did. And in our approach, we're actually doing things like that. We haven't done it. We actually did it historically for vehicles, but our hardware was so bad. We published a few papers about that, but it wasn't so impressive because it was like vehicles avoiding moving obstacles. And there's like a fancy idea that we had that if you avoid an obstacle, that you lose some time when you do that, and that you would catch up. That is, if you avoid the obstacle, that then you move faster so that you arrive at the target at the same time. That was just an academic problem. It's not actually clear why you wouldn't need that. Maybe to hit a ball, maybe like a soccer robot, but not really so obvious. But we just did it to show that we could do it. But it makes more sense when you think about arms. And I will be having this whole lecture on timing when you're looking at arms, where you want to achieve certain things in a given time. And for instance, if you're late, you want to catch up, or if you're ahead, you want to fall back to be coordinated. And that is sort of the dynamic systems analog of this year. It actually allows more things than this. Good. So dynamic windows approach is also, just to tell you very roughly, the notion is that you take as constraints things like the maximum acceleration or maximum deceleration of the vehicle, so you know how quickly could you stop and how quickly could you accelerate. Sorry. And you express the configuration space, including these kind of constraints. So for instance, here you would have velocity space. This would be angular velocity. This is linear velocity. And you're computing the boundaries. You have some sensor model, some model of the world this way, all right? Knowing the distance, you have to have some form of world model. It could be actually, in practice, could be just a depth map from your current view, and then you update that depth map every moment in time. And so from that, you could compute in velocity space where these boundaries are. That means this is the velocity so that if you're rotating faster than this or moving linearly faster than this, then you will not be able to brake before you hit that wall. That's the idea. And so if you have an assumption of velocity and you know your peak acceleration, you're assuming you peak, let's say, deceleration, then you know with that velocity and that deceleration, the time you need to hit that surface, is shorter than the time you can brake. That's how you compute that. So it's not a trivial computation. I mean, it's straightforward, but do that numerically. And then you essentially plan in this space. So there are, here's a verbal description of the different constraints, and the question is, so what they actually do in practice is they build this, I don't want to go through those things. They build these kind of potential contributions, that is, contributions over velocity space, and they have some way, somewhat ad hoc, to express how desirable values of velocity are. I don't remember if it's positive or negative. You can use either side. Let's say if it's positive, then these would be very desirable values, and the low values would be very undesirable values, just from the potential field approach, right? And so for the different kind of constraints, you can compute functions like that that express this degree to which these velocities are desirable. And these are some other, I don't remember which ones. This is for clearance, and the first one was, I guess, for getting to the target, and then some smoothing of those so that you don't change the velocity too abruptly. And then you have an overall, sum all these up, and based on that, you always choose the next velocity. So here you, like in the attractor approach, you're doing it in velocity space, right? Every moment in time, you just compute velocity, and you have to update quickly enough these kind of functions. These functions are local. That is, if you're, it's a function of a velocity space, but as you move, the function will change, right? And because now the distances are different amounts of time I need. So every moment in time, there will be a new computation. So the computation is a little bit of a limit because you have to do that in real time fast enough. And then you can also put things like desired velocities, like you want to move fast or not. Often you might want to have high speed, so you put in a desirable thing, and then it will make some compromise of that. And so they demonstrated this. This is also in late 90s, so more than 20 years ago. This was a famous robot. This was the Rhino. Somebody heard about that, the Rhino? Well, it was, this is a German group. These guys are the three German stars. I have them cited here somewhere. Yeah, Fox, Burkhardt, and Thun. Anyone knows these guys? So Sebastian Thun is the guy who then moved to Stanford and won the DARPA race with the autonomous driving. Became quite famous, the Volkswagen. And he is the co-founder of this online teaching school. Forgot the exact name of that. The first fully online university, Coursera. Coursera? Anyone knows this? Yeah, he's later became the co-founder of Coursera. I think he's still his main activity, even though he's still a professor at Stanford. And Dieter Fox moved to, was it Seattle or Vancouver, somewhere there in either North West US or Canada, I don't remember, one of those, and became also very influential in computer vision. He's also he's now heading autonomous driving at NVIDIA, I believe, this chip maker. And Burkhardt is the only one who stayed in Germany as a professor in Freiburg. He's sort of my age. He might retire soon. Maybe he's a little younger, I don't remember. So he's the last of this tribe. They were very creative guys working in Bonn. That was a famous computer science institute. And so this was in their youth. They did something, right, something fancy. So this Rhino robot was for a while in the media because it was it's a commercial robot. You buy this cylinder and there's a computer on, and there's some cameras up here, And the sensor data was actually based on sonars, I believe. So distance sensors, the sonars are terrible. They only give you distance measure when the surface has the right angle. So it's a very unreliable kind of sensor. But you have to use data accumulation, map formation to accumulate sensor information in time. If not, the sensor information is too unreliable. But it's low level. You don't have to have a lot of computation. And they had this rhino move around a museum, somewhat uselessly, which just was moving around there. You could imagine that you make this system guide someone or something like that. And you would have to have other things to do, like to speak to someone. So it was just driving around and avoiding people who are moving there, right? And dynamical obstacles are difficult. And it was not using a map of the museum, it was just autonomous. And so here's an example that it would move along a corridor and you wanted to go through this door. And these things that you see here, those would be its perception of the world. So its perception of the world comes from some echo it's got from its data. So for instance, from this wall, it got that echo, it gets some, it models the distance and the orientation of the wall. And so these lines would be its sense of the world. And from each of these lines, it would compute, the potential collision points, which speed it can go. So always this logic, which speed can I go so that I can still brake before I hit that wall, that estimate of the wall. And so there are some videos on the internet where you see that it would really drive quite fast along the corridor and then turn and go through the door to the target at impressive speed. And that was what made that famous. Now, theoretically, it's sort of really the step that we also do in attractor dynamics, going to the velocity space, aesthetic space, and to also really express constraints in that space. Good. Here's an example here. These are speeds where it doesn't turn, the very high speeds, and then if at a certain speed it does, then actually manage to turn. Go from there. It avoids humans who are dynamical obstacles. Good. And related, so the Kornstein-Born is older. It was published 91, but that was like the end line of that. And that's also related. It also used sonars at the time. And I just presented because it's conceptually interesting and it is being referred to because of that. It's no longer sort of the art. People don't literally use that, but they use ideas like that either even from laser range finding, which is much better. And so it really has this notion of detecting the direction in which you're free to move. And you will see it's sort of like the attractor direction. So it combines two problems. One problem is working with unreliable sensor information, which is also, it's also something that our approach aims to. And with a sonar, you need to do a little more work because the sonars will give you a signal unreliably. So hint is, when the orientation of the wall isn't good, you don't get a signal. And so the workaround is that you make a map of the world in terms of location. This would be this grid. And you enter into that map your estimate of how likely it is that there is an obstacle there or it's a piece of wall there. And you can, what you need to do is look at that direction from your sonar from different orientations, so that if the wall that's an orientation, there is a chance you get an echo at some point. And that's one of the things that they did, sort of like an element of SLAM. And so the certainty values are accumulated across measurements. So as it moves along, it gets from some of those world voxels here, or it's actually pixels, multiple measurements, and then it will increase the certainty about that, and from others maybe only once, and then that's how it builds the wall. And then when you have that histogram, it keeps building that histogram all the time, right? And it's just a world, but you have to know where you're in the world, so you also have to estimate your ego position. So over time, this will drift. It has a typical SLAM problem. And then when you're looking at any point, you are really making decisions about which direction to move. And that's where it's like the attractor dynamics approach. you're not planning the entire path, you're just saying which direction is a good one. And to take into account that you have some idea about the target and you have entries into your algorithm from all the grid points in the world where you know there are obstacles. So you see sort of in a directional way, for instance, this obstacle makes some counts that these are undesirable directions, this is a desirable direction. So in practice, what they did is they make a like a potential function. I think I like, where is it? I have here, this is a good one. So they in angular directions to have a count of how many counts you have for negative votes for that direction. So for instance, in this direction, there was an obstacle, and then you would add counts that so many votes of this confidence measure speak against these directions. And then they actually had an algorithm to look for minima of these negative counts. So not occluded, not obstructed by obstacles. And then they select the minimum that is closest to the direction which the target lies. So it's not exactly an attractor, but it's you can think these minima, like take the derivative of this. If you smooth that, take the derivative of this would be a potential, and take the derivative of that, then the minima will be zero crossings with a negative slope. So this would be an attractor, and that would be an attractor, and here the maximum will be a repeller. So you could make that a dynamic system. So they have this algorithm that is just not exactly the same. That is, they would just determine every moment in time which is the right minute to go. But they had some algorithmic smoothing. That is, if this jumps around, they wouldn't change opinion right away. They would make several steps and see if that direction really survives, and then only switch to another direction if that's the vote is consistent across multiple trials. So this system was working reasonably well. This is an example in their lab. They had this vehicle with sonars and had some obstacle. Here's the target, some obstacles, and so on. And this is what the histogram looks after some time. You have entries at the walls, sort of represents the world by these measures, and it was able to move around. I think this is from the same environment, and it would be able to move to the target. I don't have any. Here, this is what I was looking for. It was able then to make it to the target. And they published some papers that says that. Yes.
But they are also like restricted by how good is the control of my robot, right? Like if it's moving not as it's supposed to be, my histogram that I'm measuring is going to be wrong.
So I think what you're hinting at is that the accumulating the information across multiple locations means you have to update your estimate of where you are, so that you can adjust how you map things onto the grid. And that estimate is based on dead reckoning. That is assuming that if you send this command to the wheels, I should have moved this much. And there is always an error in that, of course. And that error is not correct. There's drift. It's a well-known problem. There's drift in your position estimation. And that means that over time, that map becomes invalid. And so that's true. And in fact, it's only, in a sense, it's like a moving window that is, what you really do, this was just a demo. But what if you really deploy that, what you would be doing is that you're overriding this map all the time. That is, so rewriting it. And so the old entries will fade and new entries come up. So it adjusts to that kind of drift. This is the core of the SLAM problem, right? In the SLAM, you want to build a map as you're moving around. And to do that, you always have to transform the sensor information you currently have into an estimate where there's in the world. But because you don't know exactly where you're in the world, you're going to make wrong entries and the map drifts over time. And there is also, the only thing is to always keep it going and to have some recency thing that older entries are downgraded over time so that you update your map all the time. Yes.
So blue closures would be a possible approach for this, right?
I didn't hear the first word.
Blue closures.
Yeah, in SLAM, so I was going to talk about SLAM next week a little bit. So in SLAM, you can also try to improve your estimate of where you are based on the map you already built. So rather than throw away the map or update the map, you could say, oh, maybe I'm not where I'm thinking I am. Maybe I'm in this location based on what I see compared to the map I already have. That's ultimately what loop closure means. That is, you're ultimately connecting. Loop closure comes from the idea if you've moved far enough so that you are at the limit of your map, and now you're entering an area where you, from some other excursion, already have some entries to recognize, this is the area where I was before, and that means you're updating now your estimate of where you are in the map based on the information in the map. Like there should be a wall here, and I sense a wall, maybe a little bit off. Oh, then I must be at that location where I'm seeing this wall, and I thought it was here, but I'm actually a little further. So I'm now updating my position based on the map rather than based on my jet reckoning. And that is actually a principle that could, that what it does is ultimately overrides. So you're just using your jet reckoning only in the short term. In the long term, you override it by being in the map. But you, of course, have to have a map for that, right? And the map was built by yourself. So it's only, works in the long run. Every moment in time has error. We actually built a dynamic systems version of that 20 years ago, and I'll mention that a little bit next week. A system that does exactly that. It throws away your dead reckoning once it recognizes something in the map that it made itself based on that reckoning, and somehow that works. It's kind of a bit mysterious. That's what you were imagining. Yes, exactly. Good. I mean, this is all 90s, right? But the technology behind that is the core of today's method. So, and the big thing that happened from this to the current approach. The current approach is difficult to present because they don't really write papers like that. It's all one big architecture, one big code, and you don't really get what the core methods are. But you can see, how they describe it, that what they do is use these kind of map formation things on much better sensors. So the big breakthrough in this area, and Sebastian Thun actually was the one who pushed that, was using laser rangefinders. So you know that, laser rangefinders? So they are like sonars, but with light. And they are, so they always get information, right? It's not, it doesn't depend on an echo. They can really find out the exact depth vector from any location. And then the more optimal way of doing this, rather with a histogram, is probability. So so-called probabilistic methods, where you use Bayesian estimation to combine the model knowledge with the sensor model, and also in some sense you do that optimally, so-called particle filters. So using particle filters, part of probabilistic methods, and better sensors led to this stuff really working quite well. So, for instance, in terrain, it's a different thing if you have traffic, right? Traffic, on roads, you have to do dynamical obstacles, you have to understand traffic routes, so a lot of other complications, right? But just the vehicle displacing itself in a world, that was solved very well. And this DARPA challenge that Sebastian Thun's team won was actually about moving 200 kilometers through, I think, some desert in California, somewhere there. Like in the military, I mean, DARPA is a military funding agency. It was based, like for military vehicles that would drive on the battlefield, right, rather than on roads. So there was later a DARPA challenge for city traffic as well. But these methods were pioneered in this formal domain. So I'm showing you this older style because it's a bit more intuitive what they're doing, but this is still the core of what the modern methods do. Yeah, the last thing I had planned. Yeah, any other questions on this? Yeah, I have more slides here you can look that up. I just want to give you an impression. So it illustrates again that sensor information, path planning, so modeling, path planning, so on, are all integrated in practice in these vehicles. And that was very long time the bottleneck, that you had to have sensor information about the world. The one product that Quan had was actually a walking stick for the blind. Actually, it wasn't ever really a real success commercially, but it was an interesting idea. I think it's kind of It's actually interesting. So they had a little vehicle that would be navigating locally with actual sonar, which was bad, better now with the laser range finder or LiDAR sensor. And it was moving autonomously, so it would be avoiding the edge of the sidewalk and obstacles. And the blind person would just follow that stick, but could sort of interpolate himself. And they had a patent for that, and they did some demos and so on. And that's sort of the spirit. It would be just a local device, right? Because the human still has a map and knows where it wants to go. It's just a local navigation on the sidewalk if there's stuff. No? Makes some sense. But you can imagine that a motorized walking stick, batteries, and a lot of things that people don't really like that. Good. And so let me just plan here. I have this here. That was my last thing, yeah. So we're fine. So this is a paper that we had sometimes used as for exercises, but it's a bit too complicated for that. And so this year I did the simpler essay. This is from the group. Estela Bicho is my former doctoral student who directs a lab in Guimarães. The address is here in Portugal. And actually Wolfram Erlhagen is another doctoral student of mine who worked in a different area in the dynamic field theory. And they met when I worked in Marseille, and Estela was my doctoral student, and Wolfram was a postdoc who stayed there for some months. And then they ended up marrying, and they're both working in Portugal on these things. And so they have pushed, this is like a couple of years ago, 2019, they have actually more projects. This is like a academic project, and they also have now projects where they actually do that in the factory floor. There is a company is from the subsidiary of Bosch, who produced something there. I don't know what it is, and they are have a project where they do that on the factory floor. They have vehicles there that transport stuff there. So interesting, and it's really pushing the technical attractor approach very far. It's really interesting. So it's cooperative robots. I should say someone called At Large in Roshina Baishi's lab. It was a famous lab at UPenn at the time in Philadelphia. Roshina Baishi is now retired, but she later moved to California. They had already used the attractor dynamics approach to control swarms of robots, but it was largely in simulation. They had one very crude real life thing, but it didn't work very well. But they worked out how you could do that. So essentially, when you have multiple robots, you could consider the robots obstacles against each other, so you avoid that they collide. But you could also give them shared information, like they all go in the same direction, or one robot follows another. You could do that symmetrically or asymmetrically. So they worked out these different things. You'd have different force lets, right? For following a robot, for going to the target, for avoiding obstacles, and so on. Hello. And so Estela Bicho and her team worked that out in much more concrete detail. So they essentially gave one robot the task of being a leader, and the other being like they called it helper. And the notion would be that they are doing really cooperative work. So in this case, there was actually something they transported, right? These are these little vehicles, like the Robodin that I showed you. This is like the scaled up version. I mean, it's not much larger. It's about half a meter circular, and they build up something on top. And it's still a PC on board, an embedded PC. Of course, in industry, you wouldn't do that, right? Like carrying something this, it would be, would build a whole piece of hardware around it. But it was the idea to be able to transport something collectively. This is the cargo here, right? And therefore to do path planning, and not to do it such that the whole configuration avoids obstacles, so that the front and the back robot avoid obstacles, and not that they coordinate it, not one just go around left and the other one goes around to the right, right? And that they also take into account that the connection between them also avoids the obstacle. So you can see that if you go with a piano around the corner, the back person has to make a wide turn, right, to avoid that you hit something there. And that's something they did with the attractor approach. So again, I'm not going to be able to explain all the details of that, just to give it the flavor. They are, these robots are really like the ones we discussed, robots that are use subsymbolic, that is sensor-based. They have these distance sensors mounted around the robot. And they have a steering two wheels and heading direction, and they are informed about the direction to the other robot, simply because the cargo is loaded on some device, and that device rotates, and they have a shaft encoder. So like if you think of the cargo being some fixed structure, wooden structure, then it's mounted on the robot, and by having a shaft encoder that knows the angle that this cargo has with the robot, you know essentially in which direction the cargo is sticking out. For the leader, it's behind. For the follower, it's in front. And that's it, right? That's the sensor information they have. So about distances, about the direction to the other robot, and then of course they knew about targets. So they assumed that they know the direction of targets. I think R is perhaps the target. Yes, R. And in practice, the target was defined. I showed you a simulation, I think, last time, where they used a colored object. So they had some simple way of determining what the target is. In fact, other activity in that group uses dynamical field theory to detect stuff like that, to estimate targets and track them and so on. And so the method, so there are a couple of ideas here. So one is just obstacle avoidance as we know it for both helper and leader. And then there is some tendency to follow the leader. And then they have a notion of a virtual target. So they have configurations that they are aware of. So this would configuration where the real target is occluded by an obstacle. And that would, now you have this problem that you don't want your rear to hit the target. Now, if this one goes around for the target, then this one would be hitting, right? This is like when you're touching the corner. Naive drivers sometimes do that, right? The back of the car can hit the corner. And what here, unlike in a car, the back is steerable because this is an active robot, can steer. And so what you actually do is you put a virtual target somewhere which would drive the back out to avoid the corner. And they have figured out geometrically, parameterized functions that are automatically just computed given the distances sensed and the target and so on, so that under, when the right angles overlap or at distances, then this virtual target gets a certain strength, and it would attract the back to turn around. And they have, and again, there is this one following term that the follower will also have a contribution to consider the front robot as target. So it would be driving behind the front robot, and these different influences have different trade-offs. And all I can say, it works. I mean, it is tuned by hand. It's nothing. It's not like this is totally high-dimensional spaces you have to optimize. You can tune it by hand by just common sense, simple limit cases. Again, always just looking at when one bifurcation happens. And so as a result, they are able to move around fairly complex environments. So here, this configuration, they're going to go around this here, around this corner, and follow a moving target. That moves. They track the moving target, and they avoid the collision around this narrow corner. That's sort of a demo of the thing they can do. One can trace that out by really looking at the dynamics of each component robot. This would be the leader, who has an attractor here and there, two possibilities, and the helper has a unique attractor, and so on. I invite you, if you search the paper, you can do that based on the slides. There's online material, and there are very cool videos. I think, do I have a video in here? No. They have videos which show that, how that works. This is actually a factory floor demonstration of that. But I just showed you with simulations. They have a lot in the paper. And then they did it in the factory floor. This is a real environment. No, that's not. complications, but not very cluttered, right? The factory environment still has enough paths for them to move. Remember, the sensory information is this infrared reflected light, so it's very low level and not precise. So it depends on whether the surfaces that light gets reflected from are reflecting a lot or not. If they are sort of bright surfaces, they work better than if they're dark and so on. But no, it really worked in real life. So that's certainly the fastest one to push that. Good. So I give you a somewhat partial review of this. Of course, if you look into the literature, you will see that there is a lot of work on these exact geometrical approaches. And then there is potential field approach, and everything else is so small, which is it's a lot, because then if you look at people who actually work with these robots, then they use potential field approach for reactive, and then the deliberate approach is often not very sophisticated. It certainly doesn't use much of that math. So you can say a lot of math has been generated, but only very little of it is being used, somewhat like an AI. And attractor approach is only used by a few heroic people who bother enough to understand that math, even though it's whenever you compare it to the other approaches, it really works very well. So it's competitive in the sense that as a reactive approach is very good, not in the sense that it's easy to program or